You have already learned to find the nature of a function in a given interval. Let's extend the concept to determine the nature of a function at a given point. Consider a real-valued function f defined on an open interval I. Let us find the nature of the function at a point x1 in the open interval I. The nature of the function at point x1 is the same as the nature of function in the open interval containing x1. Let h be a small positive real number. Consider an open interval in the neighborhood of x1, that is, open interval x1 minus h, comma, x1 plus h. Function f is said to be increasing, or strictly increasing, or decreasing, or strictly decreasing at point x1 if it is increasing or strictly increasing, or decreasing or strictly decreasing, respectively, in the open interval x1 minus h, comma, x1 plus h. Now, we will state and prove a theorem based on the nature of a function at a given point in the domain of the definition of the function. Let a function f be continuous on closed interval a, b and differentiable on the open interval a, b. Then the function f is said to be increasing or decreasing depending upon whether its derivative is greater than or equal to 0, or less than or equal to 0, respectively. And the function is a constant function if its derivative is 0. Let us prove the theorem now. Consider two arbitrary elements, x1 and x2, such that x1 is less than x2 in the closed interval a, b. By the mean value theorem, there exists an element c in the open interval x1, x2 such that the derivative of f at point c is equal to the value of f at x2 minus the value of f at x1 upon x2 minus x1. Let's consider that the derivative of f at point c is greater than or equal to 0. This implies that the right-hand side of equation 1 is greater than or equal to 0. On simplifying, we get f of x1 is less than or equal to f of x2. This shows that the function is increasing. Now, we will prove the second part. In this case, we will take the derivative of f at point c less than or equal to 0. This implies that the right-hand side of equation 1 is less than or equal to 0. On simplifying, we get f of x1 is greater than or equal to f of x2. Hence, we can say that the function is decreasing. Now, we will prove the last part. In this case, let's consider that the derivative of f at point c is equal to 0. This implies that the right-hand side of equation 1 is equal to 0. On simplifying, we get f of x2 is equal to f of x1. This equality is true for all values in the closed interval a, b. This implies that the function has a constant value for all the values in the interval. Hence, the function is a constant function. This theorem leads us to some important results. Let's take a look at them. A function f is said to be strictly increasing in an open interval a, b if its derivative is greater than 0 in that interval. A function f is said to be strictly decreasing in an open interval a, b if its derivative is less than 0 in that interval. A function f is increasing or decreasing on R if it is increasing or decreasing in every interval of R.